Yeah, let's get into the manufacturing process of the face, because I think for people to truly understand what you just described, they have to know how it's made, because we've talked about this before, and it's pretty incredible how that carbon face is actually made and what detail goes into even the bonding process, right? Let's start at the beginning. To make the face, we're talking about layer after layer after layer of carbon, right?
Yeah, 60 layers of carbon in different angles, right? So if you look at, there's two types of carbon. Well, there's lots of types of carbon. There's two major types. There's one we call pre-preg, where it's sort of single direction. So it's just like strands of carbon fiber all laid side by side. It's like almost like, just long, skinny strands. And then there's other ones where it's like woven, where you see like the woven material that looks really pretty, and like the ones we want to have on the outsides of our drivers. A lot of the materials are the pre-preg, where it's straight. And so what we do is we'll put one at like a 0 and then do like one at a 90, right? So that's like 90 degrees, and we'll do 45s and negative 45s. And then the tensile strength gets stronger and stronger as you create all these different angles or like flags of material that we do. And so you can imagine we build what we call quasis, which are a group of carbon fiber pieces that have been put in different directions, 45s and negative 45s, 0s and 180s. And then you put those all together and you can build up strength and rigidity that way. And so, we actually do a lot of testing with different configurations of the quasis when you're building up these 60 layers, right? So you'll have like 8 layers of this, 4 layers of that. And you can imagine everyone's at a different angle. As you build up, you build rigidity and strength and able to get more like trampoline effect or less. And we can put thicknesses in different areas so that we can really build something that isn't just perfectly at the limit of what the USGA allows, but like further across the whole face. Like, how do we make the sweet spot bigger, right? And we do a combination of all these layers of carbon as well as the speed pocket on the bottom to sort of have that face give. Between those two things, working simultaneously together, we can make a product that actually gets like more area of the face gets high COR. So that's really cool. The other great thing is because there's so many layers, we can control every layer. Ultrasound, X-ray, we can make sure there's like perfect amount of epoxy between each layer, so we get the bond strength that we need. But at the same time, because it's so finite and so thin each layer, we can fully control that, so that when you see the part to part, like, you really can't tell the difference between them. They all perform identical to the last one.
And the bonding part of this, I think this is probably one of my favorite stories of how that happens and what detail really goes into that. And you told us the story on the surface, and so I want to get into it a little bit more about how did this even come about, where you said it's basically a no dust room. You've got to put on a full suit, you got to go on sticky paper, you get air blown off
air chambers. Yeah, you got to go into like a cupboard almost, and you get blasted with air chambers, and you come out on the other side, and then you walk again across sticky paper, and then you're kind of met with robots, It's totally different. But yeah, so one of the biggest issues we had at the beginning of the process, like at Stealth Face, we had some bonding issues, with the product, and a lot of that was contamination in the glue bonds. This epoxy is so strong. If you look at it like it's maximum strength, you get the maximum strength two ways. One, or multiple ways, but one, you prep the material, right? So we blast it with like a plasma blaster. We laser etch it. We do all this like prep work to it to give it like a tooth for the epoxy to stick to. And then we mix the glues, right? They're part A and part B glues. And so those things have to be equal amounts of the two, right? The right amounts of the two. And then you have like a very short window to bond the material together to make sure it all stays together. In the old days, we used these really big vats of glue, because it's more efficient.
Sure.
You can make more parts within an hour. And then we also didn't have this non, static room to make the parts. And so we were seeing dust particles land on the glue, and then we saw the glue start to separate part A and part B, and so that was some of the issues. So we weren't getting like maximum bond strength per part as we are today. So now we use these very small amounts of glues. We have a clock that actually ticks off to say like these parts have been prepped, the robotic prepped, and they're going to be now put all together. You've got like 5 minutes to be able to bond the whole thing, or else you just scrap the whole head.
Wow.
And then you got to be in this dry room with this static room where there's no dust particles, so there's no contaminations now. And so once you're in there, you stay in there, the parts get bonded, and then it's like a 5-minute window for each one to be done. So like there's more time on prepping, there's more time to making sure it's all dust free, and then there's like less time to actually bond the materials. So you put those all together, and now we start to see that our parts are at maximum strength. Where before they weren't necessary. But that's part of the learning process. And we're at the point now where we really understand how to make the perfect bead around the material, the perfect amount of material. And then again, it's got no dust contaminants, and it's been mixed perfectly.
Who figured out that it was dust and glue separation? Because I know that had to have been a talking point at some point of how do we fix this and what do we do?
Yeah.
I mean, the level of detail for every single face, and then to figure out, hey, if we eliminate dust, if we make smaller bottles of glue, that level of detail to me shows the commitment and what TaylorMade is really producing.
Yeah, so we make and break a lot of products. When you break product, you look at where did it fail.
Yeah.
You know, and a lot of times there's this separation, or there wasn't enough glue in the area, or it's really crazy that there's a ledge behind the carbon, and that ledge has to be within 0.1 millimeters, or else we don't make it. It has to be that accurate. If it gets too long, you get like separation, like it comes apart. If it's too short, it shears off. And so we perfected the art of putting all these parts together, allowing them to have rebound because you need some trampoline effect in there, and then have it all stay together at the same time. It's unbelievable how many hours are spent whiteboarding with PhDs trying to figure out how to make all these parts together. And then at the other side of it, this looking at the way like apples and electronics are made, they're made in this same environment. Yep. And so if you look at where golf manufacturing is for most of the products out in the world, it's a pretty dirty environment, right? And we're bringing it into like the 21st and if not 22nd century.
Yeah.
In terms of the way we're manufacturing now is on par with how Apple makes phones, or Samsung makes phones, or TVs. And so we're just elevating the factories to that level because we can control the process so much better. And if we can control it better, the consumer is just going to get a better product.